Hello, welcome to my Tech Fun. My name is Igor and I'm actually curious about this video because I have absolutely no experience with 3D printed metal. I mean, how strong is it? Do we have that weak layer adhesion problem or something like that? And I will compare it directly with the FDM printed objects from ABS. Now all these test specimens are printed by JLCPCB, and the primary services is manufacturing PCBs, but they also have 3D printing services. And also I presented their SLA and MJF 3D printed objects. Maybe it is important to mention that this is not a sponsored video. I got these test objects for free. Well, actually I had to pay $2, and probably this is the amount how much I will earn from this video if it will stuck under 1 or 2,000 views. But never mind, my curiosity is much stronger. And before I start with the unboxing, first let's see shortly the ordering process. After logging to JLCPCB website, I'm going to Resources, 3D Printing, get an instant quote, and here I'm uploading all my files. First I'm uploading files for SLM metal 3D printing, and for each object I am selecting the printing type, quantity, adding some description, and after this I'm saving to cart, and then I'm uploading the files for ABS printing. And for each object again I am selecting the printing type. Here I can select the color too, save to cart, and then I can see the summary of my order with estimated values. But I cannot do the payment yet. Every object will be reviewed. For example, here I had some objects with thin parts, and I have to confirm that I know there is a risk of damage during the printing. And after approximately 2 weeks the package arrived. And now let's see what's in the box. This is heavy, so this is from stainless steel. No, first I will open the ABS parts. These are test objects, the test specimens. And I also ordered this Satsana fan shroud for Industry V2 from ABS. I ordered these two to test their possibilities, because sometimes this is heavy for printing. You cannot print with the supports because you cannot remove them from inside these channels, and this starts from very small contact surface, and basically the supports you need only at this part here, and this printing looks really great. And the reason I need this from ABS because I already printed this from PETG, and it melted here where the hot end don't have the covering from that silicone cover. And now these are those test objects from ABS for the bending and impact test, tensile test, layer adhesion, grip test, and the torque test. Quick check of the dimensional accuracy. 10.3 by 4.25, a little bit bigger. This should be 4 by 4 millimeters. A little bit bigger in cross section, the diameter. This should be 6 millimeters in diameter, and this is also a little bit bigger. So approximately 0.3, 0.4 millimeter bigger dimensions. So probably they use a little bit bigger flow rate. I hope this will result better layer adhesion, but we will see that in a few seconds on the testing. Now let's see the metal parts. For the feeling, definitely real metal, and it's heavy. Yes, no coin. Well, this is mostly for aesthetic look, but this coin looks great. And I have two of them. A twist drill, diameter 13 millimeters, and we will see if it can be used as a real drill. I know, to drill at least some wood. These are test objects. Oh boy, this is really strong. For the grip test, And something I predicted that if this is strong like a real stainless steel, then I will have problems with bending or breaking them, and definitely for the feeling this is very, very strong. Probably this will not bend at all. I'm not sure if I can bend it in my experiments, but this is comparison video. And I'm sure that this will not break under my half kilogram hammer. Maybe I will start immediately with the 1 kilogram hammer. Let's check the dimensional accuracy. This is diameter of 6 millimeter and this is 6.06, so very accurate. This should be 10 by 10 millimeters, 10.1, 10.1. 10.09, 4.12. So it looks like the accuracy is better actually than with the ABS parts. And just in case this is printed in vertical position to see if we have some kind of layer adhesion. But I think they didn't print this in vertical position. 2 by 2 millimeters in the middle, and this should be printed in vertical position, but I can see from this texture that this is printed in horizontal position, so actually I cannot test here the real layer adhesion, but now at least I will have 4 test specimens for tensile strength, and in all 4 cases the smallest cross-section area is 2 by 2 millimeters. Of course, this is my problem because I ordered this object. Theoretically, it should be printed in vertical position, but they oriented it in the most comfortable position for printing, and that's the horizontal one. Now, of course, these 2 cross-section areas are not equal, but to make it comparable, I will calculate the stress in megapascals or Newton per square millimeters. This means the force I will divide with the cross-section area, and in that case, the 2 values will be comparable with each other. And the reason for this is that I have no idea how strong is 3D printed metal, and I want to be able to break it with my equipment. Now, one thing I noticed that this object for the torque test is usually printed in horizontal position with FDM printing. This is printed with the bridging. And I noticed that this metal part is printed in vertical position. I can see that from this surface here. This means I will have at least one object where I test the layer adhesion, because if it is printed vertically and if it has some weaker layer adhesion or something like that, it will break here much easier. So this will be very important not only for the torque test but for the layer adhesion too. So this is not a regular bolt, it has 2 threads on it, one right and one left sided. I printed for the joke because I want these nuts left and right sided to use on one bolt. But unfortunately it doesn't work. But now I know because the size is a little bit bigger on all test objects by approximately 0.1 millimeter. So this means that I should reduce the size in X and Y direction by maybe 1 or 1.5%. In that case it will be functional. But of course I will use it, but not with this regular nuts, but I will 3D print one, which I will extend the size in XY direction by 1.5%. And in the meantime I printed these nuts. I raised the size by 3%. As you can see, it works perfectly with this metallic board. It's a pity that it doesn't work with these metallic nuts. It would be more elegant solution. Just for comparison, I'm curious about the density of this object. For the bending test, it is a box, so I can measure the dimensions, and the weight is 26 grams. Just for comparison, the ABS is 3 grams approximately. And I measured the exact dimensions of this test object. This is in cubic millimeters, but if I divide 26 grams with 3.32 cubic centimeters, I will get 7.83 kilograms per liter or grams per cubic centimeters, and this is very close to official 7.85 kilograms per liter density of the stainless steel. This means that this is really solid objects. There are no bubbles or gaps or something like that inside. And I'm starting with ABS tensile test. This test object is printed in horizontal position, and the smallest cross-section area is theoretically 4 by 4 millimeters, but it's a little bit bigger, but I will calculate it in that stress equation. Now for the feeling, this was weaker than usually the tensile strength of the ABS, but now I noticed that they didn't use the maximum number of the perimeters, but 100% infill and only 2 perimeters. Probably this made these test objects a little bit weaker than my usually test objects when I'm testing ABS or any other material. And now the layer adhesion test. This test object is printed in vertical position, and again the smallest cross-section area theoretically is 4 by 4 millimeters. And again I can see maybe 3 perimeters, and the rest is properly 100% infill. And now on the metallic test objects, don't forget the smallest cross-section area here is 2 by 2 millimeters. Theoretically, this and this one in the middle should be for testing the layer adhesion, but as I mentioned earlier, they are all printed in horizontal position. First objects are those which had to be printed in vertical position. Smallest cross-section area is the same, only it is wider on the holding parts. And these are originally designed to be printed in horizontal position, but in the middle size is the same, so I should get the similar values here. And they are broke properly on the smallest cross-section area. It was so hard to break it that I didn't watch the scale, so I don't know the numbers yet, but he already saw a few seconds ago. And now the IZOD impact test. I will start with the ABS, and here I have this half kilogram hammer which will swing to the other side, and from the difference in potential and energy I can calculate the energy used for breaking the test object. Now in this equation we have mass, which will be half kilogram in this case, we have g, the gravitational acceleration, and we have the difference in height, which has to be in meters. And I will divide this with the cross-section of these test objects, and I can get, I don't know, in kilojoules per square meters, the energy. Now with this metallic, probably it will not break under this half kilogram hammer, so I will replace it with this 1 kilogram hammer, but I have the feeling maybe this one too will not break this test object, but this is maximum what I can produce with this equipment. Okay, let's start with the ABS part. ABS. The zero position. Even the ABS was very tough material. And now this is 1 kilogram hammer. Stainless steel. I cannot see not even smallest bending on it. I want to try to mill down this cross-section area. The thickness is 4 millimeters, but I will try to make it approximately 1 millimeter, and I hope in that case I have a chance to break it with my equipment. Definitely for the feeling like real steel. And the new thickness is exactly 1 millimeter now. What do you think? Will it break under 1 kilogram hammer now? Let's find out. Second attempt with the 3D printed metal, but now the cross-section area reduced from 4 to 1 millimeter. 3D printed metal with reduced thickness. And the zero position. It didn't broke. I hope you can see it didn't even deform. So even with this reduced thickness, I cannot measure the real impact strength of this material with my equipment, but at least I know what is the minimum, but the real impact strength is of course much higher. But at least I know one more thing, and that's that it is very easy for machining. I can see absolutely no gaps or bubbles or something like that on this cotton surface. And for the feeling, that's why I like these manual milling machines. It was like a regular steel. At least I can see that it started with bending, but it was very far from the breaking. Here you can see the position of half kilogram hammer after breaking the ABS part. This value is good for filament and average for ABS material. And here you can see the equation with 1 kg hammer, and we reduced A by 1 mm thickness. But since it didn't break, this value only shows the possible minimum breaking energy. One more thing I want to try, but probably it will not be a problem. I want to see how easy it is to drill and tap a hole. It will be M6, this means I have to drill 5 mm hole. For the feeling it was very strong, stronger than the carbon steel, so definitely really great material. The hole is perfect, and now let's create a thread inside. So the cutting was really hard, so definitely harder than the regular carbon steel, again I can confirm that. And this is M6 bolt, and it works. And now 3-point bending test, but I know I will have a problem now again with this metal part, but I hope I will have some measurable deformation, and since this is comparison video, I want to see how much load I need to have the same deformation with the ABS part. Now I notice that this is not 100% perimeters, but they use some 3 perimeters and 100% infill. So this deformation is not 100% comparable with my test, where I use the maximum number of the walls of the perimeters. Well, it is better if you don't see it, but here I use all my gravitational force, and I could bend it only 0.8 millimeters. And it looks like I have some permanent deformation. And now ABS. And here for 0.8 mm deformation I needed only 2.6 kilograms. And usually I record the load for 2 mm deformation. Well, so the ABS part started with the bending and then it broke completely. And on the metallic part I can see very minimal permanent deformation. And now on regular torque or twist test, the diameter of the cylindrical part is 6 mm, but actually this is designed for the plastic, because I'm sure I cannot twist this 6 mm steel. Imagine, can you twist, I know, M6 bolt, which is actually weaker than this solid 6 mm. I'm not sure, I will do the test with the ABS and then I will think something with the steel. So this side goes into the vise. And the other side goes into this digital torque meter. It can record the peak of one movement, 1.5, oops, and 1.6 was the peak. Let's give it a try, but I don't think I can deform this, especially with this small arm. It was overloaded. I will try to reduce the diameter on a lathe machine, and I will try to calculate the stress with the new cross-section area. And now the diameter is reduced to 3.05 millimeters. I hope I can have some deformation now. And now with reduced diameter. Three 3.2, 4.1, 4.1 was the peak. And I could break it. And it broke probably along the layers, so it has some weaker theoretically layer adhesion, but anyway this was very strong. And now my regular creep test. The creeping is the deformation of the material during the constant load. These are my standard test objects from ABS and from metal, and I will place on them this 1.25 kilogram load, and I will follow the deformation in next 5 days. I will measure the distance between these two reference surfaces. It should be 12 millimeters exactly. Now I measure on metal it is 12.1 and on the stainless steel it is 12.2. But it doesn't matter because with the creeping I need the deformation, the difference between 2 days. Almost visual, no deformations here. For ABS I'm locking the position with this part here, so it can be more accurate measuring. 16.07. Now unfortunately the metal didn't deform enough, so it cannot fit inside this M3 bolt, but it is strong enough so I can measure it without deformation. 12.25. And I will repeat this measuring once a day next 5 days, and on last day I will place it inside the oven on 50 degrees Celsius and measure that additional deformation. But the measuring will be off camera, only I will create a picture once a day. So this is day 0, this is day 1 after 24 hours, day 2, day 3, day 4, and now 1 hour on 50 degrees Celsius inside the oven. 1 hour passed and actually the temperature inside was 53 degrees Celsius, and now let's measure them. And our last measuring after this heating. Hmm. 16.24, almost no deformation, no creeping. And the stainless steel 12.24, no deformation at all. And now removing of the load. After only approximately 5 minutes, almost no permanent deformations on these two objects, just a little bit on the ABS. And now let's see the possibility of this twist drill. A few months ago I created a shorty with a plastic 3D printed twist drill, and I got so many evil comments there because people don't understand really the point of that video because they don't read the text. The point was that basically that can also be used as a twist drill until the drilled object is softer than the material used for the tool. In that video I drilled the apple and it was drilled without any problems. Later, but not in that video, I tried to drill this wood even with this pilot hole, exactly this one here, and basically it melted. And now I will try to drill the same wood with this 3D printed metal twist drill. Now let's see if I can drill aluminum. This is 5mm thickness, but I will create a pilot hole with a 5mm twist drill. And I will use some cooling lubricant here. This is crazy. I didn't expect this. I wanted to try the wood, but I didn't expect that it will cut aluminum. And let's check the edge of the twist drill. Well, I'm not sure is it visible on camera too, but this edge is in perfect shape and it's still very sharp, both edges. And basically this is another proof of the great layer adhesion with metal 3D printing, because this is printed in this position, and if it would have any weakness in the layer adhesion, this could easily break along the cross section. And now let's analyze the results in this Excel table. I'm starting with the creep test, and these are the distances between two reference surfaces, but I actually need the changes between 2 days. And that's why I prepared this table. 0 means no creeping. There are some negative values, but probably that's the result of inaccuracy in measuring. And these are all very small values, even this. The tensile test. For ABS I have 2, but for metal I have 4 because unfortunately all 4 test objects are printed in horizontal position, and that's why I don't have here any. And it is very important to mention that this is the breaking load in kilograms, but I calculate the stress because the cross-section is not equal in 2 cases. And basically this is what I need for the comparison. In a graph you will not see good this difference. That's why I add here the multiplier, so this is how many times is metal stronger than ABS. For bending I don't have to change, so this is the load in kilograms, and it was very big difference here. For the impact test, this is the value for the ABS. This is average value for the ABS, but of course very good for compared to the other filament types. But metal, don't forget that here I calculated with 1 kilogram hammer and we reduce cross-section area, but even then this is only the minimum since the test object didn't broke. And the torque twist test, I calculated using these values. This is in Newton meters, and I calculate the stress, but with reduced diameter. And don't forget here, basically the diameter has the factor here in the power of 3, and this is also a very big difference. Here you can see the multiplier. Basically I can show you here in the graph, but don't forget this is very small value. I check earlier results. And here you cannot see good difference, but you can only see that the metal is much stronger compared to the ABS. Interesting that here the layer adhesion is not much weaker compared to the tensile strength. And here you can see the bending load for the 0.8 millimeter deformation, the breaking impact strength kilojoule per square meters, and this is the torsion or twist stress in megapascals. And now the conclusions. First about the ABS. Interesting, very good quality ABS, and this is the first time that on this creep test I don't have the deformation, almost not even on the first day, and especially you saw after 53 degrees Celsius 1 hour I don't have any additional creeping on this ABS. Unfortunately they didn't mention me what brand they use here, that's their secret. Only weakness I could see on the tensile test, but when I analyzed the cross section I can see they use the 100% infill, and there I can see a little bit more gaps than usually which I print using the maximum number of the perimeters. Now about this 3D printed stainless steel. The SLM 3D printers are very expensive, and that's why it is good to know where can you use 3D printing services. And now I know that this is really great quality because it is like a CNC machine stainless steel. I cannot see any kind of the weakness of these objects. And this was most impressive, basically, to use this 3D printed twist drill like a tool to drill aluminum. Of course, don't use this to create this kind of tools. Regular twist drill is much better, of course, and probably cheaper. By the way, approximately price of this twist drill would be $18, but when you upload the STL files before you do the purchase, you can see the estimated price of the objects. I'm not sure is it according to volume or maybe the Z hike or something like that, but you can see the summary before you do the ordering. Well, this was my first experience with these 3D printed metals, but definitely if I want to do more testing like this in the future, I should redesign these test objects, because my test specimens and testing are designed for 3D printed plastic and not for this very strong stainless steel. If you have any other experience with SLM 3D printing, please leave me a few lines in the comments. Thank you for watching, and happy designing and ordering. Bye!